So if you remember from last time, we were talking about the nuclear atom, right? And we were talking about how our friend and your friend, right, my friend and yours, Rutherford, used alpha particles right here, right, which actually have the same charge as what? The protons, exactly. They're the same charge as protons, right? And he used these alpha particles, he shot them on a thing of gold, and he noticed that, look, my drawing is still there. He noticed that when the particles hit the center of the gold atoms, they would get deflected. But when they went between the gold atoms, they would pass straight through, right? So that introduced to him, or that led him to believe then that the center atoms were actually positively charged. Does that make sense, right? And so that made it so that, remember the plum pudding model, which I also call the what kind of model? The chocolate chip cookie model, right? Remember that? That disproved that model because that model thought that it was a sea of positive charge with the speckles of electrons around, right? Or maybe vice versa, I can't remember. But who cares? They were wrong, right? We know now that the atom has a nucleus, a center, okay? We know now that the atom has a nucleus or a center, okay? So just a close-up look of that right there, right? And so Rutherford postulated very small, dense positive center with electrons around the outside, which is basically what we think of them now, right? It's basically what we think of atoms are now. Atoms are made mostly of space, which is funny because this table here seems like it's pretty solid. But it's actually all empty space, most of it. Like 99% of this table is empty space. Isn't that crazy? So what do you think it is that keeps your hands from not passing through the table? Does anybody know? If it's all empty space, you should be able to just put your hand through the table, right? 99% of it is empty space, right? So why do you think you can't push your hand through anything that's solid? What do you think it is? It's electrostatic repulsion, right? Because you're made of atoms too, right? You are a person, you're an object, a solid object that's made of atoms too. And what is surrounding all of your nuclei? Electrons are, right? And if the electrons of this table are negative, what are the electrons of you are? What are your electrons charged? Negative. And what does negative do with a negative? Repels, right? Like signs repel. And that's the reason why you can't pass your hand through a table. Does that make sense? I mean, you think about it, right? You go through life and you're like, oh, it's a solid table. Who the hell cares, right? At least I can use the table. At least I can step on the floor and not fall through the floor, right? But there's a reason for all of it, okay? Like, look inside, look deep into what's in this table, and it's the same thing as you. Because this table is made of wood. Wood is plant cells, right? Just like you are made of cells, right? All of our phospholipid bilayers, cytoplasm, nuclei, mitochondria. This guy might be dead, but he's still made of cells, right? And those cells are all made of molecules that are all made of atoms that all have what? Electrons, just like you. And it doesn't matter how dead something is, it's always going to have electrons, and those electrons are going to be what charge? Negative. Make sense? Right? So that's actually one of the biggest things that I think this is one of the biggest concepts that people don't get. The fact that this is the majority, this is like the center of the atom, but most of the atom is what? It's empty. Sorry, I almost hit you there. It's empty, right? It's completely empty space. All right, completely empty space. So we already answered that question last time, so you don't have to answer that one. So let's talk about the subatomic particles, right? Dang, it's already 12:08. This class goes by so fast. Sorry because I spent most of the time trying to figure out the technology in this room. All right, it's my favorite class too, so I should do it better. Anyway, protons, right, have a +1 charge. Electrons have a -1 charge, and the neutrons are neutral, right? Neutrons are neutral; they don't have a charge, right? And so, what's that chemistry joke that people say? A neutron walks into a bar and asks them, to pay the bill, right? And then the bartender goes, "For you, no charge," right? Because neutrons have no charge. Get it? See, you got to remember that on the test. You think I'm stupid right now for saying it, but you're going to remember that on the test, okay? So, protons and neutrons have essentially the same mass, right? Which you can see right here, right? Protons and neutrons, pretty much the same mass, right? 8, 7 there, 7, 3 there. To us, that's practically negligible, right? It's pretty much the same mass. But the thing to notice here is that electrons, super small. Look at that. To the -4, right? So that's 0.0005486, right? When it's not in scientific notation. So what can you glean from that kind of information? Right? What is the biggest particle? What's the smallest particle?
Neutrons are biggest.
Yes.
The electrons are the smallest.
Yes, electrons are the smallest particles, right? That's a big deal. All right, that's a big deal. Okay. This is one of those charts that you should probably, you don't have to memorize it, but just know the relationship, right? So what do we call then the atomic number? What is the atomic number? Well, the atomic number is what gives identity to an atom, okay? And so when you look at the periodic table right here, all right, I'm gonna reach over here first, over here, how about that? That'd be weird if you were under my armpit, wouldn't it be? Right? So if you look at the periodic table right here, this number right here, right, in the upper right-hand corner, those are all atomic numbers, okay? And what they do is they give the atom identity, but they also tell you how many protons are in the atom, right, or in the element, right? So what does that mean then? Changing the number of protons does what to the atom or the element? It changes the element, right? And there's no real natural way to do that, right? There's no real way to change an element to another element. You can do it with like the CERN Super Collider, right, in Switzerland, and do like a huge molecular collision. And I think I talked about this in virtual lab or virtual class, where Tony Stark made a brand new element in Iron Man 2 by making that little mini super collider, right? And then somehow he was able to fix his palladium disease he had. Remember that? If you don't know what I'm talking about, just watch Iron Man 2. Okay? So the only thing that was inaccurate about that scene was that a super collider is acres. It's huge. It doesn't fit in someone's garage, and somehow he was able to make it fit in his garage. Right?
He is a genius.
That's true. He is a genius. So, but the thing that I want you to know about the atomic number is this. It is the atom's identity, and it's the number of protons in the nucleus. Okay? You change the number of protons, you've changed the element. Okay? Make sense? There's no natural way to do that, right? There's ways that man can do it, but there's no real natural way to do it. Okay? So, let's talk about let's talk about the atomic symbols, okay? So this is carbon, right? Carbon is C. Luckily for us, the vast majority of elements on the periodic table, their symbols are basically their first initial, right? Not all of them, but most of them. And for carbon, right, it's C. And so when you look at this way of writing the symbols, right, the bottom number here on the bottom left is the atomic number. So carbon has how many protons? 6 protons, right? Don't get that wrong, because I was actually teaching a class back at St. Houston State University once, and when I asked the student there that was about to graduate with a chemistry degree what the atomic number of carbon was, they said 12. I almost hit him, right? And this guy was about to graduate. I know he was thinking about the mass, but when you're about to graduate with a chemistry degree, you should probably know the difference between atomic mass and atomic number, right? Okay, so don't get that wrong, right? So the atomic number right there, 6 for carbon, 6 protons, if that makes sense. And then the mass number. What's the mass number? Here it's 12, right? And it's 12 because it's both the protons and the neutrons together. So this atom of carbon, which we'll get into other atoms of carbon later, right? But this atom of carbon has 6 protons, 6 neutrons, right? Remember that, because there will be questions on your assignments and your exams, right, that will ask you with different elements what they mean, okay? And it's as simple as you know, if I ask you how many neutrons does carbon have? 6, because you subtract the mass number from what? I mean, the atomic number from the mass number, right? So it doesn't matter what element it is. I give you any element, right? And you know its number of protons because it's atomic number, right? You should be able to tell me the number of neutrons there are, and you should also be able to tell me the number of electrons there are. Because every element on the periodic table is neutral charge, right? It's neutral charge, right? We'll go into talking about isotopes and ions and all that stuff later, but at this point, right, if you've got a neutral atom of carbon, right, you've got 6 protons, how many electrons do you think you got?
6.
Exactly, right? Everybody got that clear? It's good stuff, right? It's so simple. So simple. To think I went to school for like 12 years to do this. So most of you here are biology degree people, right? Biology majors. And let me just tell you that to get a real good job as a biology major, you have to go to grad school, right? I mean, you can get like a lab tech job with a biology degree, right? But you want to make the big bucks, you got to get a graduate degree. And it's a good time. My dissertation was 600 pages long. So it's crazy. It's absolutely crazy, right? Well, don't get me wrong, though. My girlfriend Marla, she's got a master's in biology. She didn't have to write a dissertation. So maybe I just went the wrong path. Who knows? Right? So we already talked about that. Okay. So now let's talk about isotopes, right? Let's talk about isotopes. So if changing the atomic number, meaning changing the number of protons, changes the elements, what happens when you change the number of neutrons? If you change the number of neutrons, you turn it into a different isotope. Okay? So you see here, right, all the possible isotopes of carbon. So you remember in the previous slide, what we had was the most common isotope of carbon, which is what? Carbon-12, right? Carbon-12. Does that make sense? Okay. So 12 means it has 6 protons, 6 electrons, and 6 neutrons, right? Most common. I think 90%, let me actually look at the weight here. Yeah, like 99% of all carbon atoms are carbon-12, right? That means 6 across the board, okay? But let's look at carbon-11, which is actually quite rare, right? It's got a number here. Remember, this is the mass number, right? It's got a number here of 11. How do we get to 11? 5 neutrons plus what? 6 protons, right? So that makes 11. So that's a carbon-11 isotope. Is that what it's called? Yes, that's what it's called, right? So we get here then, we've got carbon-13, which is actually a very famous one. We use carbon-13 in NMR a lot. You using carbon dating? Is there carbon-13 in carbon dating, or is that carbon-14? I don't know. I think geology is a hunk of science anyway. But I call geology like the baby brother of chemistry. So
I have another doctor friend who would probably disagree with you on that one.
no doubt, he's probably a geologist. He or she is probably a geologist. So, but I call geology like the little baby brother of chemistry. So, oh, cute little baby brother. Cute little dog. Anyway, what was I saying? I lost my train of thought. Oh yeah, carbon-13. So carbon-13, right? Why is it carbon-13?
One extra neutron.
We have 1 extra neutron, so 7 plus 6 makes carbon-13, right? If you haven't been in school for a long time, you don't know that there's a rivalry, like a very healthy rivalry between all the sciences, all the disciplines, right? So, so it's not unusual for us to make fun of each other. So there's carbon-14, another rare one right there, which means you have 6 protons still, but now you have 2 extra neutrons, and so it's 6 plus 8 makes 14. So the big thing to notice here, right, is that the identity of the protons or the atom stays the same, right? But the electrons, the electrons also stay the same, but the neutrons is what changes. That's an isotope. I guarantee you there will be a question on your test and on your assignments that will say, right? That will say, what is an isotope, right? Or it will say, you have an isotope of carbon-13, how many neutrons do you have, right? Something like that. But it won't be with carbon, it won't be with a different element. But you should be able to tell just from what? Just from the mass number and the periodic table, correct? Right? It's that easy. Oh, look, I didn't even notice. It actually says right here, I completely guessed, and I was right. Almost 99% of all the carbon atoms are carbon-12. See, I told you I knew what I was talking about. Totally made that stuff up as I was saying it, but it turned out what I made up was right. So, all right, your first QR code question for today. Scan that bad boy. Scan that bad boy and answer the question. We'll see the distribution in a second of how you answered this question. And I know everybody's got to sign in because I have to do it too. It's a pain in the butt. We used to not have to do that, but now we have to do it, which sucks. Oh man. See, they tell you that you should bring drinks into the class. You got to keep your mask on, but I'm like, I get so excited about just chemistry that I get so hot, parched. And then there was this one time I was at the lab, my forensic lab that I work at, and I told my friend, man, Mike, I'm super parched. And he goes, oh, really? Dang, I'm really hungry too. And I said, all right. And this guy was a scientist. That wasn't Alabama though, so that says a lot for the Alabama primary education system. So, you guys must be tired of something, because that joke usually gets people laugh. Who's a snicker? Or something. They're like, damn, who's Dr. No working with if they don't know what parched means? Parched means thirsty, by the way. It doesn't mean hungry. You see, that's the joke. He said, dang, I'm hungry too. But parched means thirsty, right? I feel like you were a lot more active online than you are in the classroom, which is unusual. It's weird because normally, I get a lot of feedback in the classroom because, man, I talk a lot. But it's a good thing that's what I get paid to do.
First day, give it time.
It is the first day. That is true. Well, not the first day for you guys. You had to go to lab last week. So, which I feel bad for. Yeah, really, I do. Let's see here. Let's see how people answered this question. I expect everyone to have gotten this correct because I harped on it for like 10 minutes just now. And if you got this wrong, I promise I won't tell anybody. Seriously, guys, seriously. Do I even work here anymore? Does my stuff even work anymore? Like, what's happening here? It's amazing how much you have to go through just to sign onto a computer here. Really? Did this already this morning. There's like that little checkbox down there that says don't ask again for like 30 days. Does that even work? What is that even for now? Because it always asks me no matter what it is. If it's been a couple hours, it asks me.
It's like one of those read-capture things just to make sure you're not a robot.
Yes, because so many robots want to sign into my account and look at my PowerPoints because they're so awesome, They're trying to pirate it for other classes. And I understand that completely because my PowerPoints are amazing.
Hey, Russians or something else.
I know, man. I know. I'm totally aware of piracy out there and piracy of my PowerPoints and my QR code questions. That is a real problem that we have to deal with. I have to deal with. If you were wondering. You probably weren't wondering, but I'm going to tell you anyway. Okay, so, 13 people in the class. Wonderful. I wonder where all the other 3 people are. All right, so here is the distribution. The distribution right here. 12 people of the class. 12, that's carbon 12. Look at that. How ironic. 12 people in the class did B. 1 person did A. And let's see here. We'll go back to the laptop. All right. Picked a atom with the same element with different masses. Good job. See, that means you guys are paying attention. You may be a little quieter today than normal, but you're paying attention at least, right? That's what that matters. That's what matters, right? Just reassure me and say yes. That's what matters. That you're paying attention. All right? Yeah, good. Okay, so now that we've talked about the atomic mass and neutrons and isotopes and all that stuff, right? Let's talk about atomic mass units, the AMU, right? As we already know before, right? Atoms have extremely small masses. The heaviest known atoms have a mass of approximately 4 times 10 to the negative 22. That's 4, right? With 21 zeros in front of it. That's really small, right? Really, really light. That's like the heaviest atom. Crazy, right? Like, and everything's made of them. It's crazy, right? So on the mass scale, right, the atomic level is used where there's an atomic mass unit, and that's called the AMU. Atomic mass unit is AMU, right? And one AMU equals 1.66054 times 10 to the negative 24 grams. So that's 1 with 23 zeros in front of it and a decimal point grams. I mean, that's like nothing, right? That's like nothing at all. That's basically zero, okay? But everything we have, everything we do is made of that. It's kind of crazy, right? Absolutely kind of crazy. Okay? That takes us to atomic weight, okay? So not to be confused with atomic mass. Those are two different things, right? If you learned back in elementary school and high school, right? Mass is something that is constant throughout the universe. You have the same mass here on Earth as you will have on the moon, as you will have on Jupiter, regardless of gravity, regardless of anything, you always have the same mass, right? But you will have a different weight on all those places. In fact, if you weigh yourself on Earth, and then you weigh yourself on the moon, you will weigh 1/6 of what you did on Earth. So you want to lose weight real fast, just go to the moon, weigh yourself, take a picture for Instagram, be like, hey, this is my weight, right? TikToking while you're going up there, right? It's a good time. Sure, you'll get a lot of views, okay? The same thing is true here with atomic weight and atomic mass, right? Atomic mass, right, is the number of protons and neutrons added together. But the atomic weight, though, is actually an average of all the isotopes together, right? And that's why, when you look at carbon-12 right here, right, notice carbon-12, or carbon right there, its mass is 12.011, right? Why is it 12.011? Because 99% of all carbon atoms are carbon-12, right? So that 99 right there fits where? Right on top of the what? To move up to the next one, 13, right? You add 99 plus that right there, 12.01. What do you get? 13, right? So literally, it's an average of all of the carbon atoms, right? All isotopes: carbon-11, carbon-12, right? Carbon-13 and I forgot what the middle number was. 13 and 14, right? Hey, I'm good at chemistry, not math, right? To the dismay of my parents, I should be really good at math, but I'm not. I don't know why people think Asians are supposed to be good at math. Like, I'm totally not that. So, I mess up the head math all the time. Anyway, so you see how it doesn't say 12 even, does it? Right? It says 12.011. That's because only 99% of carbon atoms are carbon-12. That 1% right here is everything else. Make sense? That is true of every other atom there is, right? Every other element. All those atomic masses up there are a huge range, right? Of isotopes that are average of isotopes, okay? I almost said acetopes, sorry about that. I'm trying to be better about passing. Pretty good leave, you know? I had to clip out all those cuss words I said in class, in the virtual class. Which I don't think worked because now we have transcription and it's a word and I can't even figure out how to delete the words and it's a mess. Anyway, anybody know how to delete the transcription? Like just words in the transcription, not like the whole thing? So you know then that when it's that close to 12, that means most of it is what? Carbon-12. Let's jump over to nitrogen, right? What's nitrogen's mass? 14.0 what? So what is most of nitrogen? 14, right? Most of nitrogen is 14, okay? What about this one? Chlorine there, right? So that's, most of it is 19, right? Does that make sense? What's up? Oh, you're having trouble seeing? You want to move over there?
I can see, I just can't see that the last row.
Maybe we should move over there. I feel bad for leaving sewer so I apologize. Your classmates came, and that's what it should be. You know? I wanted to single out the Silurians because, you know, but that's okay. Anyway, okay? So, yeah, move up to that one up there. That one. That way at least everybody's like in the front. And then, believe me, it'd be very helpful to you when you're taking the exam and stuff, because you need the product table. So you didn't know the product table is like the best cheat sheet there is. Okay? Yeah, but see, you see how close things are? Now look at this, look at chlorine. Chlorine is 35.4, right? So interestingly enough, chlorine's mass distribution is like, is 1/3 chlorine 35, right? And, sorry, not 1/3. 2/3 chlorine, 2/3 135, 2/3 of it is 35, and the other part is 37, right? We'll talk about that in a second. But see, so you can actually even estimate what the abundances are just from the mass weight, but you can't tell exactly what it is. Does that make sense? Right? Good stuff, okay? What time is it? Dang, I swear. Oh, right here. Do this. See, I was just talking about mass weight before, right? So this here is actually what we call a mass chromatogram. We use it in forensics a lot to do things like trace analysis, drug analysis, that kind of thing, right? And if you were to shoot some chlorine into a mass spectrometer, right, it would actually break apart, okay, into these two isotopes, chlorine 35 and chlorine 37, right? And so, as I was saying over there at the periodic table, right, look how chlorine 35 is 2/3 larger than what? Chlorine 37. Does that make sense? Right? Chlorine 37. By the way, this is not how they figured out these mass weights back in the day. They did this way before there was ever a mass spec, right? But these things are super helpful because whenever I was talking about Pablo Escobar a lot recently in our class, right? Was that this class I was talking about? Yeah, watching Narcos and how it should be called stimulantos and all that. Remember that? So after Pablo Escobar was killed by Steve Murphy and Pedro Pascal, I forget what his name was in the show. The next group that came up after them that became the huge drug runners in Colombia were the Cali cartel, and they were run by Rodriguez. What's his name? His first name, I can't remember his first name. But they were the Rodriguez brothers. Well, so chlorine gas is something that's used in the making of cocaine, right? And one of the brothers' son, right, was tasked with disposing of leftover chlorine. Okay, and so what he did was, he didn't know a damn thing about chemistry, and so what he did was he decided that he was going to let the gas go into like the pipeline, like kind of throwing it down the drain, but like instead of going down the drain, it's freaking chlorine gas, it kills you, right? So it went into the pipelines, and then it started going to these people's houses, like through the drains, right? And it killed these people. These people died from chlorine poisoning. And the reason they were able to tell that it was actually chlorine is because they took a sample of the gas, threw it in the mass spec, and the mass spec doesn't tell you, Cl and Cl, right? It just tells you there's this much here at 35 and there's this much here at 37, right? And so this is a classic textbook example. Even if you don't see, right, the Cl at all, if you don't see those at all, if you see these two peaks at 35 and 37, and 35 peak is 2/3 bigger than 37, you know always that it's a chlorine molecule or chlorine gas. It's never different, right? That's how you can tell that it's chlorine. Okay?
So if there were like multiple peaks, that would indicate that there were multiple different elements.
Exactly. Absolutely. Different molecules and stuff like that, right? But yeah, that's what happened, right? And it's crazy. I mean, I don't know why you would think that. Do you guys know why chlorine gas is so dangerous? It was actually used as a chemical weapon in World War I by Haber. Does anybody know why it's dangerous? Huh?
It forms phosgene.
Sorry, one more time.
It forms phosgene.
Forms positive?
Phosgene.
Phosphine?
Phosgene.
No. But it does form something else that's dangerous, right? So chlorine is actually insidious. It's quite insidious. It's so insidious that it will steal electrons from like a kitten, like literally. Chlorine would steal electrons from a kitten, right? And the reason why it steals electrons from a kitten is because it's in the 7th group over there, right? And you haven't learned this yet, but you will. All atoms, they all aspire to be noble gases, okay? And what it means to be a noble gas is to be a member of the 8th group over there, right? Helium, neon, argon, krypton, xenon, and whatever the RN is. I don't know what RN is. Neon, who knows, right? No one ever studies anything that far down, right? So what that means is that they have 8 electrons on their outer shell, okay? And we'll get deep into that later, right? But since chlorine is in group 7 over there, right? It's only got 7 electrons in its outer shell, right? And so it's like, oh my God, I really want an electron from anywhere. You'll see what it gives, rat bastard, right? And so what happens is that when you breathe in chlorine gas, what is there abundance of in your pulmonary system and inside your lungs? An abundance of oxygen. What else? Water, right? If your lungs were dry, your throat were dry, you'd be coughing all the time, right? So tons of water in your lungs. So chlorine will go steal a hydrogen from one of the water molecules just to take its electron, making hydrochloric acid, right? And so you breathe in the chlorine, you think everything's fine, until your throat starts burning, like you just threw up after a night of drinking, right? But then it's worse though, right? Because it's worse though because you're not actually throwing up, you're actually breathing in chlorine gas. It's going into your lungs and it's creating hydrochloric acid inside your lungs. It's just literally burning out all your alveoli, all your pulmonary tissue, all that stuff, right? Like that's how insidious chlorine is. Okay? Most people know chlorine from in their pools, or they know chlorine from sodium chloride, right? Let me just tell you, sodium chlorine, they make such a great couple because chlorine is one of those take kind of people, right? But sodium is one of those give type of people, right? And sodium right here, right? It's in group 1, which means it's got 1 extra electron to give away, right? So it's like, oh man, I just want to get to a full outer shell. So please just take my electron. Just take it. And what does chlorine say? Hey, no problem, I'll take it. And guess what that makes? Sodium chloride, which is table salt, right? Which is funny because sodium by itself is also very dangerous. It's explosive. You've got to keep it under oil. Because if you don't keep it under oil, it will mix with water in the atmosphere and explode, right? But you put the 2 bad boys in the periodic table right here, the sodium and the chlorine, put them together and they become table salt, something that we can't even live without, right? Because you have saline in your blood, right? Your blood is like a certain percentage of salt. If you didn't have that certain percentage of salt, you die, right? So it's amazing how the 2 bad boys in the periodic table are like that, right? Separately, they're very, very insidious and dangerous. But together, they're just a happy couple, right? But it has to be a thing where one is taking and one is giving, And some other ones, they're much more like greedy than chlorine is, right? You take oxygen for example. Oxygen needs to have 2 sodiums, right? So oxygen is not happy unless there's a menage. Not at all. Oxygen's got to have 2 people to make it. So 2 sodiums makes oxygen happy, right? Because it's in group 6. Group 6 is mixing how many electrons from 8? 2 of them, right? So sodium has 1 extra electron. How many sodiums does it need to be happy? 2 of them, right? So oxygen is only happy with a threesome, right? Does that make sense? Unless it binds with something else that has like 2 electrons to give up, like magnesium. Because magnesium is in group 2, right? And since magnesium is in group 2, it has 2 electrons to give up, then oxygen and magnesium can get together and they're happy. There doesn't need to be a menage or a threesome, right? So this is the basis of ionic bonding, which we'll talk about in a second, right? I have no idea why I went on that tangent, but we'll talk about that later. Back to this stuff. Oh, because we were talking about chlorine. and why chlorine was so dangerous. But yeah, so when we see this on a mass spectrum, right, where you have a peak at 35 and a peak at 37, and the one at 35 is 2/3 larger than the peak at 37, or you could say the peak at 37 is 1/3 of the peak at 35, you know you have chlorine gas, right? Make sense? I bet you learned something new today. See, now we can go to like a party and be like, did you know that if you did a mass spec of chlorine, it'd show you a 35, 37 peak that are 1/3, 2/3 of each other? It's amazing. That's good stuff. Go on Jeopardy one day. They'll ask you the question. All right. So your next QR question. Okay. What is the atomic weight? Is it the total number of protons and neutrons in the nucleus of an atom? Is it the total number of electrons? Is it the number of protons of an element? Or is it an average mass of all the isotopes of an element? Whew. I'm starting to perspire. It's not good. Getting hot. Getting too excited. But this is not the end of my day either, because after discussion, I got to go set up the lab for my forensics class. And we're teaching them about blood spatter today. So we're going to have like these styrofoam heads that are filled with blood. They're going to have like crowbars, and they're going to hit the thing and blood spatter everywhere. It's great. It's a great time. Great time. So you should take my forensics class. It's a good time.
You need to get watermelons. Those are always fun.
Yeah.
Big mallet. There you go. Blood spatter.
Well, the problem with that, though, is that watermelons are chunky, you know, and when they spatter to make spatter, they're very chunky. I need to have the very specific blood spatter patterns so they can measure them, find the convergence and all this other stuff. And the other problem with watermelons, too, is that when you're doing a stabbing, you know, it doesn't do the right cast off, you know, blood spatter.
Hit
So,
somebody in the head with a giant mallet and their head explodes.
Yeah,
That's
that's
not gonna
true.
be, that's not gonna be nice and
No.
simple. It's gonna be chunky.
absolutely, well, you know, that's true, but there's still be blood spatter around, like that you can analyze, right?
So they're gonna stab it?
Second?
Are they doing the stabbing?
They're doing what?
Are they doing the stabbing themselves?
Yes, absolutely. Absolutely. We're setting up the thing in the lab so that they can, inside like this plastic room, like they do in Dexter, right? And so they'll have like styrofoam heads that they can hit with like crowbars and bats. And then we'll have like a plastic body that has like a heart inside that has blood in it. They'll stab you know, get cast off. It's gonna be great. It's gonna be a good time. So, yeah.
Just mimicking murder.
Huh?
Just mimicking murder.
Exactly. But the reason why we're doing those is because next week's lab, I'm setting up a crime scene and they're gonna have to solve the crime scene, so they're practicing blood spatter analysis. So, you know, it's a great time. All right. Man, they better appreciate it too, because it's a lot of work. Look, it's a lot of work.
You gotta stab multiple things, you gotta
Hit multiple things.
lie the body.
Exactly, that's what I'm saying, man.
It's an art.
It is an art.
Murder is an art.
And it's a good thing I've investigated multiple murders, gunshot wounds, but not stabbings. And so I get very close to those kinds of things. What are we at? Oh, atomic weight. Ha! Wrong one. See, you guys should all take my forensics class. It's a good time. Except it's not a, what's it called? A majors class. It's not a majors class. It's more of like a,
See if you can get it as a dual credit, making it an art credit also.
I've got one person that hasn't done it. Who hasn't done it yet? Huh? I've got one person that hasn't done it yet. There's only 12 responses. There should be 13. Then how did I get 13 on the last one? That's weird. That's weird. Ghost did it. Oh, maybe it was somebody on the chat. Maybe it was somebody on the chat. Okay. Wow. We have a whole hodgepodge of answers this time. So this is the distribution right here. This is the distribution right here. What is atomic weight? Most of you said D, which is the correct answer, because D is the average of all the masses of all the different isotopes of an element, right? Huh?
But you just said that weight wasn't the same as mass.
It's not. Mass is the number of mass is the number of protons plus neutrons. Weight. Sorry, say it again.
I'm sorry, how is it how is it an average of a mass then, if it's atomic weight? How does that make sense?
I don't understand what you're saying.
Can you show me the answers again?
Yeah, absolutely.
Yeah, how is it an average mass?
Yeah,
If it's atomic weight.
because like carbon 13 is a mass, carbon 12 is a mass, carbon 14 is a mass, and carbon 11 is a mass. And you average all those together, and that gives you the isotope.
Okay, so what was the answer?
The answer is E.
Okay, I'm good.
Does that make sense?
It doesn't, but I'm not sure why I'm not understanding. You know, I don't understand how we're going from mass to weight.
Oh, so I'll get to you in just a second, Mom. So mass, right, is the actual number of neutrons, right, of every single isotope. Does that make sense?
Yes.
Right? So carbon 12 means that there's 6 neutrons, carbon 11 means there's 5 neutrons, carbon 13 means there's 7 neutrons, carbon 14 means there's 8 neutrons, right? So you average all those up, and then that's when you get the weight, right? So mass is just the mass of an individual isotope, right?
Right,
But then the weight is an average of all the isotopes together.
I got you.
Does that make sense?
Yes, it does.
Yes, Bella?
Go back 2 slides.
Sure.
I think it's 2 slides.
Sure. That one? Yeah.
You didn't finish explaining. That part, that's why I explained. Point 3.
Oh, yeah. So this is just a long way of saying average, because this sign here means, it means summation, right? Summation. And then this is the isotope mass, which is the 14, 12, 11, and I almost forget one. 11, 12, 13, 14, 14, right? Right? And then the fractional abundance for all isotopes, right? But the thing you need to know, right, because I'm not gonna ever ask you to actually figure out a weight, right? I will never make you figure out a weight, but I will ask you what the definition of atomic weight is. Does that make sense?
Yeah.
Right? So I will never make you go through and actually, because there's some up there that have a bunch of, isotopes, and it's just, a pain in the butt to do. You just need to know in your head what actually a weight is compared to what a mass is, right? A weight is the average of all the masses of an isotope. A mass is the actual number of neutrons plus the actual number of protons. Make sense? Right? I mean, I could put those kind of questions on the test. Do you want me to?
No.
So I'm here to please. So if you
I've had a class that did that, it's not fun.
we could, I could totally make you do the calculate the atomic weight for technetium. You want to do the atomic weight for technetium? That's a great time. Just kidding. No, I definitely do. That's a lot of work, and that's not important for me to teach you, right? Because no one is ever going to ask you to do it. You know why no one's ever going to ask you to do it? They're on the periodic table, right? And I'm one of those people that believes that if you can just look it up, there's no need to memorize it, okay? So, and in every single chemistry class that you ever you're ever in, and in every single chemistry lab that you're ever going to be in, there will always be a periodic table. So what is the point of teaching you how to practice making, calculating the atomic weight? You just need to know what it means, okay? All right, any other questions? Dang, we only got 15 minutes left. This class goes by so fast. It probably doesn't go by fast for you, but it goes by really fast for me. Okay, so this is the periodic table. We've been talking about it a lot lately, right? The periodic table is a systematic arrangement of elements. Elements are arranged in order of atomic number. This guy named Mendeleev, I think it was a Russian, he came up with the periodic table a long time ago, before we even knew what a mass spec was, before we even knew what atoms were, all right? And somehow he was able to predict all the weights and all the masses and all the numbers for all these elements, right? And then leave spaces in between for missing elements that they had not found yet. And this is before we had any technology. So in Russia, there's actually not a billboard, a mural. There's a mural of the very first ever periodic table, and it looks very similar to that with just missing spots. And this was like 100 years ago. So if that guy can do it without any phones and calculators, you can do it too. Okay? It's great. Good stuff. right? So let's talk about the periodic table and the parts of the periodic table right here. I wish this was a little bit bigger, but that's okay. All right, we have periods, okay? Those are the horizontal rows right here. Those are called periods, right? And then you already heard me say before that the vertical rows are called groups, right? And the group number actually tells you, like see group 7, 8, group 6, group 5. The group number tells you how many electrons there are in the outer shell of an element or an atom, right? That's not the total number of electrons. How do you get the total number of electrons? If it's neutral, then it's what? The same as the number of protons, right? But if it's not, we'll talk about that later. That's called ions. We'll talk about that later. But it tells you, the group number tells you the number of electrons in the outer shell. So if you look at oxygen, for example, its atomic number is 8, and it's in group 6, right? Which means it has how many electrons in its outer shell? 6 of them. How many electrons do all elements want to have in their outer shell? 8. It's called the octet rule, right? So what does atom need? What does oxygen need to become a full shell? 2 electrons, right? Make sense? So on this side, right? On this side of the periodic table, these are called the nonmetals. Everything in the light blue here, right? They're called the nonmetals. And on this side, the group number tells you, right, how many there are in the outer electron shell. Okay? And so all you have to do is subtract it from 8, and you know how many it needs now to be what? A full shell. On this side, these are the metals, right? This is the alkali metals, the alkali earth metals. Same thing. 1A, 2A, right? Those are the numbers of electrons in the outer shell, right? And if sodium, for example, has 1 in its outer shell, right? And its atomic number is actually 11, right? What does that mean? That means it has already a full shell, right? A completed full shell, and it's got 1 extra electron just floating out there that it wants to get rid of. Does that make sense? And that's why it's so happy to give it away to chlorine. Does that make sense? Or give it away to water when you want to have an explosion, right? So, alkaline metals, alkaline earth metals, noble gases, halogens, haptogens, maybe? I think, right? But the thing that you really need to know is that the group numbers tell you how many there are electrons in the outer shell. And another way of saying that is valence electrons, okay? How many valence electrons does an atom have? It's the same thing as the number of electrons in the outer shell. And that's told to you by what? The group number on the periodic table. Make sense? Right? That will be far more important to you than the period number, okay? I mean, there are trends with the period number, but in this class and your next class, that's going to be used the most, the group numbers, okay? The group numbers. So, reading the periodic table, right? We talked about this a second ago, right? Here's krypton. No, that's not krypton. What is that? Potassium. Krypton is Kr. Potassium right here, right? Potassium has an atomic symbol of K. Its atomic number is 19, right? And its atomic weight is 39.0983. So what is the most abundant isotope of potassium?
39.
39. See, how do you know how to read the periodic table? Isn't it great? See, you're going to be better than any of those biology majors out there right now. Better than the school. Okay? Any of them. Okay? Okay. Okay. The rows on the periodic table are called periods. We just said that. These are the horizontal things. Right? The columns are called groups. You said that already. The elements of the same group have similar chemical properties. Right? So, elements of the same group have similar chemical properties. I wonder why that is. It's because they have the same number of valence electrons. Does that make sense? The reason why elements of the same group have very similar chemical properties up and down the periodic table is because they all have the same number of what? Valence electrons, right? So fluorine, chlorine, bromine, all 3 of them, right? They just need 1 more. It's going to be 1 more and I'm happy, right? And so they go about doing that in very similar ways, right? Does that make sense? Okay. It's good stuff. good stuff. This next one isn't quite as important, right? Isn't quite as important, but there's this thing called periodicity, right? And this is as you go across the periodic table, there's a pattern, right? It goes non-reactive gas, soft reactive metal, right? And then non-reactive gas, soft reactive metal, non-reactive gas, soft reactive metal, right? And what that means is that there's always going to be a noble gas right before a what? A reactive metal, right? Like so, for example, here this is lithium. That's that's super. Well, we were talking about sodium, so we'll just go to the next here. So right here is neon. That's a noble gas. It has 10 electrons. Oh my gosh. So neon has 10 electrons, right? It's a noble gas. How many electrons does it have in its outer shell?
8.
So how many does it have in its inner shell?
2.
Exactly, right? So all atoms that have more than 2 electrons have what? 2 electrons in their inner shell. So for the inner shell, what is a full shell? 2 electrons. Make sense? So it's 2, 8, 8, 8, and so on, right? So for neon, sorry, not for neon, for helium then, what does it take to have a full outer shell? Just 2 electrons, right? Because it only has 2 electrons. For hydrogen, how many electrons does it need for an outer shell? 1 more, because that will make it 2, right? It's only those 2 right there that have 2 that you care about in the inner shell, right? Everything else is going to be inner shell plus the valence. Does that make sense? Right? So you just learned something new today, unless you already knew that, right? The electrons are in shells, right? And the innermost shell holds what? 2 electrons. The outermost shells hold what? 8 electrons. All elements, atoms rather, all atoms want to achieve what? A full outer shell. Whether that's 8 or 2. Does that make sense? But it's only 2 for which 2 atoms? Those 2 there, right? Does that make sense? The ones that have less than 8, basically. Make sense? Right? So for lithium here, right? Lithium here, it's got 2 in its inner shell. It's got 1 extra. What does it have to do? Lose 1. Right? Just like sodium has to lose 1. Does that make sense? Okay? All right, so sodium is here. I said before it's a reactive metal, right? Because it combines with water and it explodes, right? And so it's always going to be, and I'm not going to test you on this because it's not that important, but just notice that there's a pattern, right? There's a pattern. There's always going to be a non-reactive gas next to non-reactive metal, right? Non-reactive gas next to reactive metal, non-reactive mass to, and it's all going to be in the same row, right? Not super important, but the pattern is not important, but what I told you about the pattern is important, okay? So what's more important are the groups. What's more important are the groups. Oh, I was right, they are called calcogens. See, I don't have to get a refund on my degree. It's crazy. Anyone ever told you that before? Well, I guess I've told that to people before. I've told that to other chemists before where we'll get into an argument about something and they say something stupid and we're like, dude, you need to go back to your school and get a refund for that degree because you didn't understand. Which is kind of neat. But these are PhDs talking to each other, right? So if you were able to get a PhD, you know your stuff. It's kind of an ingest type of thing, right? That's been told to me a couple times. Is that like a common thing? I don't know. Anyway, so groups, right? We have 1A, that's the alkali metals, the lithiums, sodiums, potassiums. I forgot what the argon is. Rubidium? Is it rubidium?
Yeah.
Rubidium. See, I have a PhD in chemistry, I don't have these memorized. So don't think that you need to have them memorized. Okay? There's no reason for you to memorize the periodic table when it's up there. Right? Beryllium, alkali earth metals, beryllium, magnesium, calcium, strontium, barium, and radium? Radium, thank you. Yeah, radium's interesting. Radium is what killed people in the watch factories. Right? Did you know back in like World War I, there was this group of women who were working in watch factories, and they were painting the faces of watches so they would glow in the dark. It was like a perfect like glow so that a soldier could see the watch face and would see what time it was, but it wasn't bright enough for like enemy soldiers to see. Right? The thing was that these women were like painting these watch dials, right, not knowing that radium was like radioactive. And so they like, lick their brush and then take the one face dial, do this all day long, 8 hours a day, right? And then they'd lick the paintbrush, just keep on licking, and then there's sometimes they would go and break. And they would put it on their faces like it was eyeshadow and stuff, and eyeliner, to make their eyeliner glow and stuff like that. It was a great old time while it was happening. It's always a great time until your jaw falls off, because eventually, right, they had to come, like, it was like 10 years later. It's one of those insidious things again. Radium is radioactive, so it's super insidious. And so like 10 years later, all these ladies, their jaws started falling off of their bodies. And they were in like their 20s and 30s, right? And no one knew about it. No one knew why this was happening until a forensic scientist and a medical examiner named Charles Norris, not to be confused with Chuck Norris, but Charles Norris, the medical examiner of New York, first one, and then Alexander Gettler, right? They were asked to investigate why all this group of girls in their 30s had their jaws falling off, right? And so they investigated, and what they did was they took their jaws and they put it on the special photo paper that absorbed radiation, and it would change the color of the photo paper wherever the radiation was emitting, right? So they took their jaws from the grave, right, like 50 years after it happened, put them onto photo paper that would react with radiation and turn different colors, and then they took the bone off, and you would see shadows of the actual bones and the jaws on this paper. And what Gettler said was, it's amazing how 50 years later these jaws are still glowing. Like, it's amazing, right? So be careful, radium. And also, I don't know why I said be careful, radium. You're not like playing with radium right now, are you? but so radium was actually discovered by Marie Curie, right? And if you know who Marie Curie is, she's like a famous chemist / physicist. I was actually honored to have been able to go to her gravesite, right, in France, in Paris, at the Pantheon. And her husband is there too. They were both Philip, I think his name was. Philip, no, that's not right. Philip Curie, I think that's right. I like Marie Curie more anyway. Anyway, so the both of them were buried there, but they actually ended up dying from radium poisoning as well, right? But they discovered radium, and they said it was radioactive, but these factories never actually acknowledged it, and so the people who worked there ended up all dying from radiation poisoning, and then also losing their jobs. The reason why they were losing their jobs is because they were licking those paintbrushes. You know what I'm saying? Crazy stuff, right? Chemistry is important. I'm telling you, right? Okay. Well, this is going to be your last question for today. My stories take up too much time. Which of the following groups of the periodic table is also known as the alkali metals? And after we get done with this question, you guys can take a break for 15 minutes, and I will meet you guys downstairs in 206. At least that's whoever that guy is over there sitting with that. I hope you y'all enjoyed the first lecture face to face. I'll let you guys have a little pass on being low energy today, since it is the first day. But Wednesday coming around, better be more energy. Okay? Better be more energy. Oh my gosh, you're right. There is only 12 people in here. Told you I'm not good at math. Okay, one more person, and we'll see what the distribution is. Still waiting for that one person. Still waiting for that one person. Who hasn't done it yet? This time I know someone not done it yet because there's only 11 responses. Should be 12. Where was that?
I thought it was 206.
Is it 206?
I don't know, my paper says 203.
Oh, that might be right.
Oh, Jesus. Do I need to check? I'll check real quick. Hold on. Oh, there we go. There we go. Wait, that's not it. Yeah. 203. Okay, so I'll meet you all in 203 after I show you the distribution of this group here. There we go. All right. Almost half and half. Well, no, actually not. It's like 2/3 to 1/3, right? A versus B? The answer is in fact A, right? Because A is the 1A is called the alkali metals. So remember that 2A is actually the alkali earth metals, right? And the alkali metals are actually more reactive than the alkali earth metals are, right? And the reason why is because they just want to get rid of those that one electrons in there. Makes sense?